Okay, I have open now the walkthrough for the H review, and this does count as a quiz grade. I have my Stapplet open, and I also have a calculator handy if I need it. So, use the normal distribution to estimate the requested probabilities. Of the objects in a recycling stream, 35% are plastic. Suppose you draw 50 objects from this stream, determine the following probabilities. So first of all, we need to know what the expected proportion is. It should be the same. So this should be a super easy question, 0.35. Standard deviation is a little trickier. Actually, let me pull up Cami in here so I can pull up the formula. And we'll just do a new page. That's fine. So the standard deviation, I'm going to kind of type it up just like a formula. Okay, so standard deviation for proportions. Cancel. Go away. Okay, for proportions is square root of p times 1 minus p, all divided by n. All right, so let me see if I can mouse draw that for you real quickly. So it's square root p, can also be q, 1 minus p. Pretend that's it. I'm drawing with my mouse, so forgive me, please, all over n. And the n is in the square root. So what does that look like here? So I'm going to take p is 0.35, but first I've got to do the square root, which is second square root 0.35 times 1 minus 0.35. So you don't have to subtract it. You can just go 1 minus. Close the parentheses and then divide by our sample size, which is 50. N is 50 in this case. All right. Hit enter. And I'm going to say it's 0.067. How many hundredths? Oh, so it's like 0.07, but I'm going to say 0.067. I won't get dinged. So the probability so let's go ahead and make sure my values are correct. It's a good idea, since I give you more than one shot on these problems, to submit to make sure these two values are correct. All right. So I'm going to go ahead and put this in, and then now I'm going to go to my normal distribution. All right, I don't need my calculator anymore. My mean is 0.35, and my standard deviation is 0.067. I'm a little, I prefer having that 0.067 there, because if I just did 0.07, that might actually put some of my values off. So I'm a little more comfortable with that on that one. All right, so calculate the area between the two values. So actually, I want to find the probability of 20% or less. So I'm going to go to the left, 0.20. And you can see it's right about here. So it's somewhere around 2%, I'm guessing. 1.2%. So just take that decimal, 0.0126, and put the whole thing in. So we'll double check it just to be safe. You'll notice your review is not super long this time, so just make sure. 0.0126. Let's see. Probability, that should be correct. I have 20%. I wonder if it's 0.07. 0.07. Let's try that. Calculate area. 0.0161. Let's see if I actually rounded it in this case, which I might have done, actually, because this was a warm-up question from years ago. And let's see how we're doing. No, everyone's going to cheat. What's going on here? Key. 0.013. So let's put it back. 0.067. Maybe I used, no, it can't be 0.06. So 0.067, plot distribution. To the left at 20%. 0.0126. It was 0.0126, but because this was a warm-up question, it wasn't dynamic, I didn't have a range. This is not registering as correct. Hold on a second. So the 0.0126 on this one, don't worry, your test is going to behave better than that. That rounds to 0.013. So expected you to round to the correct thing. So if it says round to the thousands, pay close attention to that. And be careful with your standard deviation. Let me do 0.07 just to make sure it's working okay, because this was a warm-up with specific numbers and no randomization. Yeah, see, you really wanted that to be 0.067. All right, and the key is showing it as 0.0674. which is weird that I said round to the hundreds. Who knows? Oh, I know why I said that. Okay, so let's get back to our right values. So now that I know I'm good there and I need to pay attention to the rounding, I'm going to say 40% or more. So let's go to the right of a value, 0.40, calculate the area, and you get 0.2278. So I'm going to put this in, and usually my WebAssigns behave pretty well, but this is a very static question, so it may be kind of extra picky on the answer. Oh, it took that one. It took that one. Okay. Next one, from 32 to 40% of the objects, so then I can say between two values. The reason, yeah, I know why that one was not clicking so well. You won't have that problem, I promise. Okay, 0.32. So we want between 0.32 and 0.40. Calculate area. And I'm getting 0.4451. Now you'll notice that doesn't quite match the answer key, and that's okay. That's all right. Okay. So there we are. We are getting the correct answers. And again, that's because that number is so low, and that's why I was being a little extra picky there. Okay. Actually, I'm going to turn off the key. There we go. All right. So now let's go to the next one. Suppose X has a normal distribution with mean of 53. So here's the hint. When you see these, you can just say, oh, the mean's always supposed to be 53. Okay? The mean should not change. In fact, I don't even know what this problem is. Well, actually, that one looks weird. All right. Submit. And you can see my means are correct. Now we're going to do a sample size of n is 4. So what would happen to the standard deviation? Well, I'm basically using a new formula, which is for means, okay? So the mean of, or sigma of x bar for an average is basically your old sigma, so you see how it has a sigma there, divided by square root of n, okay? Square root of 4 is pretty simple. It's 2, but I'll go ahead and use a calculator. So we have standard deviation is 15 divided by square root of 4. Enter. So 7.5 should be the correct answer here. Then we change sample sizes here to 16. So we're going to take that 15 again, take your sigma, divided by square root of 16. By the way, that's 4. So we should get 3.75. And this one's actually the easiest. Square root of 100 is 10. So I just do 1.5. Huh? 1.5. And hit submit. Wow, we made a lot of progress. Won't take very long to walk you through this review. All right, and voila, you're all done. Okay. So how do the X-bar distributions compare for the various sample sizes? Well, the means are all the same, but the standard deviations are getting smaller with increasing sample size. That looks like the first statement. The means are not changing, means are the same, and standard deviations get smaller. So it looks like all these other ones are incorrect. The main thing is, notice bigger sampling size means smaller standard deviation. Voila. Okay, now we're going to get to do some math. A new one. So this is probably a lot like one of your questions you might get on your test. A new muscle relaxant is available. Researchers from the firm developing the relaxant have done studies that indicate that the time lapse between administration of the drug and beginning effects of the drug is normally distributed with mean mu equals 38 minutes and standard deviation sigma equals 5 minutes. So we're going to administer to one patient randomly. All right, so that means we're going to go to your normal distribution. Our mean is 38 minutes, and our standard deviation is 5 minutes. All right, we'll plot the distribution, and we want to know for one person. So if it's just one person, we keep the same standard deviation. All right, what is the probability it's 35 minutes or less? So that would be to the left of 35. Calculate area, and I'm getting 0.2743. All right, we'll go ahead and submit. Voila. 0.2743. Now we're doing a random sample of 10 patients. So what does that mean? I have to take that 5 and I have to divide it by the square root of my sample size to get my new standard deviation. So this 5 is incorrect. So we're going to go 5 divided by second. Pretend I can hit second, square root of 10. All right, enter. So now I have to put this standard deviation right here. Usually if you have 3 sig figs, that's pretty good. All right, I'm going to do 1.58. And that tightens up my distribution. And now you can see 35 minutes is down here. And if I calculate my new area, it's much smaller. It is 0.0288. All right, let's make sure that's right. Voila. So the probability in part B is smaller than part A because the standard deviation is smaller for the averages. As we go bigger, our standard deviation gets smaller, which means that 35 minutes is really far away in standard deviations when we start averaging for bigger samples. When we're doing an individual, we were using 5. When we did the group of 10 patients, had our standard deviation went all the way down to about just over 1.5. All right, a large tank of fish from a hatchery is being delivered to the lake. The hatchery claims that the mean length of the fish in the tank is 15 inches and the standard deviation is 6 inches. A random sample of 59 fish. By the way, so you see these red numbers? Red numbers usually mean you got to do this calculation on your own. So pay attention and follow along. So the mean, all of us probably have the mean of 15 inches. So I'm going to put the 15 inches in there. But my standard deviation is not going to be 6. If I did 6, you can see there's my standard deviation, but I'm taking an average. So I have to divide by that 6 by the square root of 59. 6 divided by square root 59, enter. And we get 0.781. Sure, that sounds good. 0.781. Plot the distribution. All right. So now I have my model. My model's done. What is the probability that X bar is within 0.5 inches of the claimed population mean? So you're like, oh, what does that mean? Well, that means that what is it between 14.5 and 15.5? So I'm going to go right here. That my average is within ½ an inch of the actual mean. So I'm basically going from here to here. See that? 14.5 to 15.5, and I'm getting an answer of 0.478. See, 0.478. Let's go check it out. Hope it's right. And voila, that's it. Looks like and it's actually not that long a problem, is it? So, okay, a random sample of n equals 36 scores is selected from a population. Which of the following distributions definitely will be normal? We don't know that the scores in the population will form a normal distribution. For example, one of my fellow teachers at Cedar Ridge was showing me her scores, and it definitely wasn't normally distributed. It was almost trimodal. You had a bunch at the bottom, some in the middle, and then a couple at the top. So it was very odd. Now, on the other hand, if I looked at the means, that should be good. The distribution of the averages. So the scores on the populations mean I'm looking at individuals here. Sample means looks like I'm looking at the average for 36 people, and that should be good. The scores in the sample, who knows what they'll be? You never know. So it should be the sample means will form a normal distribution. So we'll go ahead and submit that. Okay. Voila. Okay. Use a normal distribution to estimate the requested probabilities. It is known that 82% of all new products introduced in grocery stores fail or taken off the market within 2 years. If a grocery chain introduces 67 new products, find the following probabilities. So, let me make sure. Hopefully I fixed this question. Hopefully I did. We'll see. All right. It used to be a different kind of question. I'm like, we're going to find out if Mrs. Zimmerman did that correctly. All right, so we know that P is 0.82, so I'm going to put 0.82 here, 0.82. And then I'm doing standard deviation for proportion, so that's sigma p hat. Pretend that's a little p hat. That's what I'm using. So I'm using that. So these guys, you really want them on your cheat sheet, and they should be on the board, hopefully. All right, so my N is 67, P is 0.82. So using that formula, I'm going to go second square root, 0.82 times 1 minus 0.82, and then divide by the square root of the divide by the sample size, which is 67, ugly number. So I'm going to get an ugly number, 0.0469. So I'm guessing I'm going to just put the 0.0469. It's better to go a few extra decimals than smaller. 0469. All right. It's better to be more exact, more precise. So there's my distribution. So within 2 years, 70% or more fail. So I'm going to take to the right of, and I'll say 0.701. Calculate the area. And I get 0.9944. Gosh, I hope that's kind of high. I always get, actually it should be okay. Pretend I can type in the right numbers. All right. And then we're saying within 2 years, 86.6 or fewer fail. Oh, that's probably to the left of 0.866. Remember to change those percents to decimals, people. And I think that's 0.8367. Let's hope that's good. See if we have any rounding issues for the question that Mrs. Overman tweaked. Are they correct? Are they correct? That one's correct. This one, within 2 years, 0.866 to the left. I'm going to cheat. Let me go see what's going on here. Turn on the key. Could be a rounding issue, in which case I need to check it before it becomes part of your test. 0.8367. Let me look. Could be it's just being too precise. 4694. Let's try that. Calculate area. Oh, wait. And it's going down. Maybe it was a 0.47. So you want to get, again, play with these. If you're having trouble, see, I'm still getting about 0.836. 86.6% or fewer fail. So that's more, guys, answers, well, 0.8347. So I would have just said try that. And I will see if I can adjust the tolerance if you haven't done that one yet. So it's a little nicer to you. I know how to do that. So anyways, it should be closer to that. I'm going to try and make sure that if you're within 0.8 here, that it will give you the correct answer. So I'm probably going to go edit this question after I finish recording this video. How about that? Good news is the first question has exactly the same answer, so you can just copy those off. All right. So I have to go edit that question. Luckily, I learned how to do that today. All right. Under what minimum conditions is it appropriate to use a normal distribution to approximate the sampling distribution? That's really the sampling distribution for proportions. Well, we know that N has to be less than 10% of the population size when sampling without replacement. We know N times P has to be greater than 10, and N times Q has to be also greater than or equal to 10, technically. Yeah. And then samples were randomly taken or treatments were randomly assigned. So these two are part of the same condition. These are called the large counts condition, and this is called the 10% condition. So if I was doing my cheat sheet, I would basically write these things down. That large counts condition for proportion, NP and N times 1 minus P. In other words, successes and failures are greater than or equal to 10. All right. 10% condition, N is less than 10% of the population when sampling without replacement. If you're doing an experiment, it actually doesn't count. It doesn't matter. Okay. Interesting. And then random, you're either doing random sampling or a random assignment for an experiment. So those are the other things I would add on to an experiment, onto your cheat sheet. Experiment. There we go. I can speak. I can type now. Sometimes doing math and typing, my brain shorts out. Okay. Finally, last but not least, suppose we have a binomial experiment in which success is defined by a particular quality or attribute that interests us. Suppose that n is 86 and p is 0.3. Sounds like I need my calculator. Can we approximate p hat by a normal distribution? So we're just kind of going through these same conditions again with you. So I'm going to take that 86 and multiply it by 0.3. And my value is 25.8. All right. Let's do it by 86 times 0.7. Basically, pretend that's the times. Or I can just say 1 minus 0.3 if I'm not sure what it is. Make sure you put parentheses around that. And I get 60.2. By the way, both of those values should always add up to n. Should always add up to n. So let's make sure we did those calculations right. And there they are. All right. So yes, because both of these can be approximated by a normal random variable because both NP and NQ exceed, and our special number is 10. It's 10. In the old days, we used 5 in this class, but everybody else uses 10, so I don't know why they do that. So what is the mean for p hat? Well, it's always just the proportion, 0.30, so that's a super easy one, all right? And let's see, what is the standard deviation? I'm going to have to use that puppy again. So be prepared to keep typing that one into the calculator. Second, square root. P is 0.3, and I'll tell you 1 minus 0.3 is 0.7, divided by our sample size, which is 86. And I've got 0.0494. That shouldn't hurt. That should be fine. Technically, I could say 0.049. Yeah. All right. Now, suppose n is 15 and p is equal to 0.2. Can we say approximate p hat by a normal distribution? Well, we're going to say no. And why am I going to say no? Well, if I go 15 times 0.2, you see the answer is 3, right? And we cannot use a normal distribution because NP does not exceed 10. It has to at least be 10, all right? And can we approximate 72 and 0.40? I'm pretty sure we can. 72 times 0.4. So they're having us calculate those values, 28.8. And then I'm going to do 72 times 0.6. That's 1 minus 0.4. Right? That's my expected number of failures, 43.2. So that's good. So we're going to say yes, we can approximate it because both NP and NQ exceed 10. All right. And we're almost done. Then I'll actually calculate. Oh, this is super easy. P hat is 0.2, and then I'm going to do that calculator thing again. Second square root, 0.2 times, and I know 1 minus 0.2 is 0.8, divided by, and our sample size in this case is 72, 0.0471. Pretend I can type. 0.0471. Submit. Use 3 decimal. What are the values of mu p hat? Oh, I didn't use the right one. I used the 0.2. So let's do that again. 0.4. Let's do the right square root. This is why we double check. This helps if Mrs. Everman is reading the right problem. Right? We're doing 0.4. We're doing sample sizes of 72. There we go. Let's do that. Let's try that one. 5, 7, 7. Submit. And there you go. Helps to do the right problem. Okay, so again, there's your cheat sheet if you want to take a quick shot of that. That should get you through most of it because you've got those two rules right there. You know how to use Stapllet with the normal distribution, so it shouldn't be too bad a test for you. It should be a quick and easy test.